So for the past few hours, you have gained all the foundational knowledge on SNOMED CT, and now for the rest of the day, it will be all the fun stuff, because now we'll start to explore SNOMED in more details, and we try to start doing retrieval. First, we're going to do retrieval of SNOMED CT concepts, and then in the afternoon we're going to play around like data analysts. So here in this part I'm going to introduce expression constraints, and we're going to together try to do some expression constraints. This will be repetition, like we have concept definitions. The first part before the circles comes are the parents, the subtype relationships. So here you see that in the diagrammatic view that Kai was just showing you. So they are supertypes, not subtypes, sorry. It's the parents. And then we have the defining properties there. You always see that it's a defining property because you see the yellow ellipse here. That's the semantic relationship. So these concepts are defined using the concept model. I spoke about that earlier. And this concept model provides value because it provides the validation rules. It's the foundation for processing and for effective retrieval, as you would see now. I was saying earlier that we have a range of relationship types, and here's just an overview. We have actually more than hundreds of defining relationships or attributes. And if you recall, some apply to some domains, and each of them have specific ranges. Here's the example we looked at before. The domain is the source domain, so clinical findings can have a finding site, and the value of that finding site is with the anatomical or acquired body structure, which is in the body structure hierarchy. And this is important when we start to query, because maybe we want to be very explicit about what defining properties we set as criteria for our query. So these general rules, they are manifested by relationships. So a concept such as pneumonia, which is in the clinical finding hierarchy, have the finding site of lung structure. And here you see lung structure falls within the range of the rule for the range of that attribute. These expressions, you see them here in the diagram. And as we also just saw, Kai was showing you in the expressions tab of the browser, you can also represent the definition of a concept or the inferred definition using an expression. An expression in the SNOMED terminology, an expression is a representation of a meaning, of a clinical meaning. And we have a syntax, which is called the compositional grammar. And this grammar is designed or specified so that we can accurately describe the definition of a clinical meaning in a computer processable manner. And there is a long form that includes the terms. So this syntax here, the red parts is really the notation for the compositional grammar. And then we have the compact form here, which is easily computer processable, but harder for humans to understand. So that's why we both have the long and the short form. If you want to learn more about the compositional grammar, you go to snomed.org/SCG. So all concepts, when you look at a concept in SNOMED, and think about the pneumonia example I showed you earlier, that it has an associated morphology of inflammation, it has a finding site, that can be represented as an expression. And that is what makes, facilitates the computer processability. So that's where you saw the expression in the browser. So here you have an example of the simplest of three simple form of expressions. So essentially you can say that a concept ID, just a concept ID, that's also a very simple form of an expression. It's just referring to that single concept. But you can have the same meaning represented as an expanded expression as you have it here, with malignant tumor plus malignant neoplasm plus neoplasm of lung. And then we have the curly braces here indicating the role group, the group of attributes, the finding site that equals the lung structure, and an associated morphology equals a malignant neoplasm. So that expression actually means the same as this very simple expression over here. It's just the expanded version of that forms the definition of that pre-coordinated expression here. And it's the same for cyst, excision, and for any concepts in SNOMED CT, we have a corresponding inferred definition. So when we talk about pre-coordinated concepts or pre-coordinated expressions, that's just an expression using a single identifier. But you can also have a full expression, or in this case, the expression representing the inferred definition. So every time you hear the term SNOMED CT expression, that represents a single clinical idea. Okay, it's just one clinical idea. So that's the basis for understanding then expression constraints, because where each concept can be represented using an expression constraint is a language that we use to specify a computable rule to define a set of clinical meanings, potentially a set. So where expressions are about a single clinical meaning, expression constraints are about defining rules to define a set of clinical meanings. So here's an example. And this language, the expression constraint language, ECL, that builds on top of the compositional grammar. So it has many of the same notation and structure, but it builds on top of it. So it has its own additional features, and it's a range of additional features actually. But this is an example of an expression constraint where we want to use to extract all the lung disorders with a morphology of a type of edema. Okay, so think about the example I showed earlier today where we want to start looking at our clinical data. If I want to see how many lung disorders do we have with the morphology of type of edema. So those questions that could have a clinical value to get answered, that's what we start to formulate now. And I can represent that in a computable, processable manner using this notation here. So I'll say all the subtypes of disorder of lung with an associated morphology equal to descendants or self of edema, so any type of edema. Think about the back injury example, any type of back injury. We can extract it very easily here by just the 2 consecutive single less than signs. Then the terminology server will execute this expression constraint, and it will look at the inferred definitions of the concepts in SNOMED and find those that match this criteria. So find all the concepts that are a subtype of disorder of lung that has exactly an associated morphology with a value that is a edema or any subtype of edema. And then that will result in a set of concepts. And this is really the computer processable power of SNOMED, that we can easily define, this is the criteria, these are the concepts we want to extract. When we do execute expression constraints, we have a substrate. You have just heard about the various editions and versions of SNOMED CT, and SNOMED CT can evolve. So it doesn't matter if you're using the international edition from January 2024, or if you're executing it against the January 2012 edition, because concepts may have been inactivated and been added. So the substrate is quite important. And you need to be aware of what substrate you're using when executing an expression constraint. And then you have the expression constraint, which specifies the criteria, and we call the result of the expression constraint, the executed expression constraint, the expansion. So the expansion is a set of concepts that match the criteria. So generally, expression constraints will follow a structure like I show you here. There can be one or more focus concepts. So starting. So if we just have one focus concept and none of the ECL symbols, then our expression constraint is restricted to that single concept. But in this case, we have a constraint operator, the single less than sign, which means I want to retrieve all the subtypes. So it's all the subtypes of clinical finding. So the first part of this expression constraint specifies that we want to explore not procedures, not body structures, but all the concepts within the clinical finding hierarchy. We also have another focus concept, which is the cardiology reference set. It's an example reference set. And then for that, we want to use the member of function. And we use a conjunction between the two. So the first part of this expression constraint says that give me all the concepts in SNOMED CT which are types of clinical finding and are members of the cardiology reference set. So imagine that you have created a subset that consists of both concepts that are organisms, procedures, findings. So you have a big cardiology reference set, which includes a mixture of concepts. But now you want to extract those members of the cardiology reference sets that are only clinical findings. That's what you would get from this. And not only do we want to have the concepts returned that match that criteria, we want to refine it even more. We want to say, well, give me all the clinical findings that are members of the cardiology reference set and have an associated morphology that is a type of infarct or are associated with a myocardial infarction. So as you can see here, these criteria, associated morphology, associated with, and the values for these, they require that those constructing this expression constraint have some idea about what types of relationships. So depending on your use case and the people defining these expression constraints will need to have a more or less in-depth understanding of the relationships. It's easier with those very high-level expression constraints where you just want to say, give me all the subtypes or give me all the parents, give me all the children. But if you want to really utilize the defining properties, you need to have an understanding of the attributes. And also if you want to even more specify that they need to be part of a group. But this diagram really shows the range of features of the expression constraint language. In addition to this, the expression constraint language also support filters. So we could even, in extension to this, also say, well, within the concepts that are returned here, only match on those concepts that have a certain synonym or have a certain effective time. So you can apply a range of filters as well. This is just an overview of the features of the expression constraint language.
I think it's worth mentioning that the expression constraint language is designed so that it can be implemented in any technology, that it can be implemented in databases or terminology servers, using any language. So it really uses the structure of SNOMED when it's published using the inferred relationships. And when we say descendant of, we're really talking about what's lower in the hierarchy. We're not using an owl reasoner to do subsumption in real time, which would require a lot of memory and computing power. It's not that. It's just what's lower in the hierarchy. As the hierarchy's already been created, it's already been published, it's set. So yeah, it's really about going up and down the hierarchy and filtering using attributes. It means that you can just run it in a database and it should work. Or a terminology server may only need 1 gig of RAM instead of at least 4 if you're using OWL.
Okay, so that was all of the basics of ECL for you today. But let's now try to look at how it with these examples I showed you before. So this is a simple expression constraint, descendants of disease. So what the ECL engine would do is to match on the first two expressions we have here, because these concepts are all subtypes, so lower in the hierarchy. So if we look at these concepts in the browser and traverse up, we would see that one of the supertypes of these concepts is the concept disease. If we refined the expression constraint to say, give me the concepts that are subtypes of disease and have an associated morphology equal to descendants of cyst, then we would have only the cyst of kidney being returned. But look at here, I said equal to, I could have said equal to cyst, but here I say equal to descendants or self of cyst. So here are two concepts that match. Cyst of stomach, they have an associated morphology that is equal to cyst. Cyst of lung also have an associated morphology equal to cyst. But in the expansion, we would also get a concept such as ganglion cyst of right ankle returned, because that also matches the criteria. But here the associated morphology is not cyst, it's ganglion cyst. But that concept is a subtype of cyst. So because we said, I'm going to scroll back now, because I said descendants or self of cyst, I take everything that has a defining property that is some kind of cyst, not only cyst. So this is where we use the accuracy of the modeling we allow for the accurate concept modeling while still being able to query them. Here are some different examples. If we're wanting to find all the clinical findings that are findings and disorders located in the left arm, we could do it using the expression constraint you see here. We can use exclusion to say lung disorders that are not a type of edema of trunk. Before we saw the conjunction where we use it and, we can also do the exclusions. We can also use the any operator. So give me any concept that has some finding site that is not a hard structure. It supports cardinality. So give me all the pharmaceutical products in SNOMED CT that have 2 or more active ingredients. We can use the filters to specify exactly what types of map record we want to look at. So in this one, give me all the members of the map to ICD-10, but where the map target is J45.9. So this would return all the SNOMED concepts that is mapped to this code in ICD-10. We can also get all the members of a subset that has been added or changed after a specific date using the effective time. So with these filters, it requires us to understand the headers used in those map reference sets or reference sets. The example down here, subtypes of disease with a description, you can see how we have a description filter where we are looking for diseases that have a certain term with a substring of hard at. And we can also, and that you'll see later, query over inactive concepts. So often we get the question, but when things changes in SNOMED CT, should we then also change our records, the things that have been recorded using SNOMED CT? Would we have to keep that up to date? And the short answer is no, you don't. Your terminology server should make sure that you will include those concepts in your queries. And that's what this filter is for. We have a guide and specification, and particularly chapter 6 in this specification includes a range of examples that's really good to refer to. We also have an appendix that's like a quick reference. So if you're one of those who are going to do a lot of ECL, I would certainly advise you to bookmark the specification and guide. Even though it's a specification, it's also a very practical resource because it has a range of examples. So now it's your turn to be active here. I'm going to skip over this part, and I think we should get started. There are 2 main ways to construct expression constraints. If you have the in-depth knowledge of the defining properties and the syntax, then you could use just an editor, as we have it in the browser, a text editor where you can populate the expression constraint. Or you can use a builder that has been designed to support that. And the SNOMED CT browser includes both. So if we go to the browser again, where you were before, One of the things here in the right-hand side that Kai didn't show you because he was saving that for me is the expression constraint queries tab here. And that's a place where you can just type in the expression constraint and then execute it. But now you know that we can't remember the SNOMED CT identifiers. They are not intended to be something that you can remember. So the feature here is that you go in and search for the things you want. Let us do what Kai was doing before. Diabetes, it's okay. Diabetes mellitus. And you can see here some of them are red because I've searched for both active and inactive. So I'll just do for active and we'll take diabetes mellitus. All those yellow circles here, you can drag them. So you drag them into the text field. I think you should try it. Just drag a concept. It doesn't matter which one. And if you go to the help button here, if you can't recall the symbols, you can see here what they do. So let us take the very common one, which is the descendants of, which will give you all the subtypes of diabetes mellitus. So you just enter the single less than sign. And then you click execute. And then you can see that there are 133 concepts in SNOMED CT that are subtypes of diabetes mellitus. If I pick diabetes mellitus here, go to the taxonomy view, and I put descendants count on, I drag it over, we can confirm. So here you see the concepts in the taxonomy view, and you can see there are 133 subtypes of the diabetes mellitus. So the same result that we got here. So this requires you to know the symbol and know what concepts to search for. We can try the ECL builder as well. So we go into the ECL builder, and then we can also see here we get a bit more help because here you don't have to remember the symbols, you can see them. So if we wanted to, instead of finding all the subtypes, but we want to find all the direct parents of diabetes mellitus, parent of, so not all the subtypes, only the direct parents. That's what we get here. And you can see the output has been updated to use the new one, and I can click OK. And now it has updated the expression constraint here, and I can click execute. And there are 2 parents of diabetes mellitus here. I want to show you another thing before we go to the exercise for you. I'll go back to the descendants of diabetes mellitus. We found 133. Let us go back in time and see how did it look in 2012. So now I swapped version. I'm still in the international edition, but I swapped version. And I can see here that in 2012, we have the same expression constraint, and I'll click execute. At that time, we had 91 concepts, active concepts in the international edition matching this criteria. So that's how you can swap between the various versions. I'll go back to the presentation now. And let's do some exercises. The question is for you to tell me how many concepts are returned when you follow these steps. You go to the browser, select the international edition. I should have said what version. Use the latest version. So the April 2024, isn't that the one that's on the browser? Yeah. And then you do a search for pneumonia. And you want to find all the subtypes. If you guys just, how do I do that there? Guys just mentioning that you can actually swap the display language for the SNOMED browser. So you can actually choose French. If you don't like the English terms here in the actual browser, you can swap to French. Do you have the answer? No? Do you have a question? What did you say? 183. So let us confirm. We do a search for pneumonia. Will I get the right result when I execute this, do you think? I won't. No, you're right. Because I'm in the July 12th. So I'll jump to the current. And you're absolutely right. So well done. 183. I hope those of you online who are following are applauding yourself for getting the right result as well. In the next one, you should go to the ECL builder. And you should select the focus concept surgical procedure. And then you should add a refinement to specify a procedure site of any thumb and a method of any type of excision. Here I've helped you in saying what kind of attribute or relationship. A procedure site, a thumb, and a method of any type of excision. I can just, if I go back to our pneumonia example, here, to add a refinement, I click refinement. So if I wanted to say, well, what could it be? A pneumonia with some kind of, Ian, what could we refine this with? Yeah, we could actually specify a site, couldn't we? That is some type of lobe. A type of, yeah, but we could refine it to say, well, pneumonias. Okay, so a pneumonia caused of some kind of bacteria. Yeah, domain. So I'll just do search for bacteria. There's many domain bacteria. So that's how you can specify refinement. And then I execute and we find 83 types of pneumonia that are caused by some kind of bacteria. So that is how I use the ECL builder. You just click add refinement. So back to the task for you. You want to find any surgical procedures with a site, any type of thumb, and a method, any type of excision. I hope you will follow along as I go through this. Go to the browser. We want to find any type of surgical procedure. And then I want to add a refinement. So if I were to say, I want the finding site, I don't get the option to select this because a surgical procedure can't have a finding site. And this is one of the benefits of using a dedicated ECL tool like this, that I can't make mistakes in what kinds of attributes I can use. Remember, I showed you we had a concept model and we have some computer processable representation of that. So this can be applied in a tool like this to say, give me all the attributes that are available for this domain that I've chosen here, surgical procedure. So I want to specify the site. So I just click site and then I get the options that match on site. And then you can see we have 3 different. In this case, you would need to understand the difference between these. They can be, that is documented again in the editorial guide. But here, because I know that procedure site has an attribute hierarchy, it makes sense for me to say, well, give me any type of procedure site with a located in the thumb. I'll take the thumb structure here that comes up first, and a method, some kind of method, measurement method or method. And then, was it an excision I said? What is excision? Excision, the action of an excision. While I've been doing this, it has constructed the proper ECL down here. I'll just click OK, and now you see it populated here, and I'll click execute. And there are 18 concepts in SNOMED CT that are types of surgical procedures located in any kind of any part of the thumb. When I select the thumb structure, it includes excisions of the entire thumb or any parts of the thumb. And we match on any type of excision action. So if we take any of these 18 concepts, amputation of thumb tip, you can see that it has been defined with a method of amputation and a procedure site direct thumb structure. If we go to amputation, you can see that that's a subtype of excision. So that matches the criteria that we wanted, concepts that have been with the finding site of the thumb structure, any type of thumb structure, and a method of some kind of excision. Yeah, we are not going to go. So I'm being reminded that we have that we don't have any more time, but there are more exercises here that I advise you to go through. We have included the actual expression constraints, so you can just copy them into the ECL and then execute them and try to do it on different versions of SNOMED. It's quite interesting to see. It becomes very clear that how generic it is, that you can just apply it, and how SNOMED CT is designed to be. It's a standard. You can use it on any version, any edition. Then we have a set of slides on the use cases for these expression constraints. And since we developed the expression constraint language, we have just been amazed by its importance and its many uses. Its expression constraints are super powerful for implementers who want to specify value sets easily. Earlier we were talking about some registers that capture cardiovascular or cancer registries, who have a range of sets that they want because they are using very structured documentation. And you can use expression constraints to maintain a large number of sets and to generate them and maintain them easily. You can use a expression constraint to define the criteria for your map. For example, when we map between SNOMED and ICD-10, we map between SNOMED and concepts within the clinical findings hierarchy. So you can constrain, well, in this map, I don't want the map targets to come from specific areas of SNOMED CT. I want to specify that it's exactly these concepts. So ECL is useful for maps and translations as well. In user interfaces, they are particularly useful. I'll just show you an example. And we're going to show you this example in more detail tomorrow. But in a clinical user interface where you may have a diagnosis field, you want to ensure that you can't capture procedures or pharmaceutical products or anything. So this field in a user interface can be constrained using the expression constraint language to make sure that the things that you capture falls within the domain. So if I search for appendicitis, I get clinical findings. I don't get procedures. If I search for under the procedure field that has been defined to all the descendants of procedure, and I wanted to say appendicitis, you can see I only get appendicectomy or other types of procedures that match this search string, I don't get any clinical findings because this field has been constrained by the expression constraint language. So this is really also powerful to support data entry. It's also supporting clinical decision support rules. So if the disorder or if the pharmaceutical products that I have selected have this active ingredient, then trigger this alert. And as you'll see after the lunch break, it's incredibly powerful when we want to do different types of clinical data analytics. So Kai and I are going to talk you through that in the afternoon. The following slides here really just shows you these examples of you can use it to maintain subsets. If you have a subset of mental disorders that you are implementing and you want to make sure that you update it over time, you don't have to manually add the concepts that have been added. You just execute the criteria for your subset over against the new substrate, the new version. We have mapping tools that support ECLs in defining the scope. We have different examples of how you can use it in terminology binding, like I just showed you in the UI tool. And the data analytics I'm not going to talk about now because we'll do that later. And these slides, which you have also available in French, also shows how different types of decision support rules can be implemented using the expression constraint language. For example, linking to clinical guidelines, trigger alerts, and so forth. Yeah, expression constraints in a nutshell. It's yeah, I hope you now feel like you know where to go to start playing around with expression constraints, at least. Mm-hmm. Are there any questions?
Thank you. So maybe it will come later, but I was wondering if there was an API to send these ECL queries to SNOMED so we get programmatically the answer.
Yeah, after the break, I'll introduce terminology services and we'll go over that. But yeah, FHIR will be the primary way.
On peut préciser aussi qu'en France, on a un serveur de terminologie. Ce serveur de terminologie implémente aussi des interfaces FHIR et qu'on est en train de travailler justement pour que vous puissiez passer une requête de type GET dans lequel il y ait derrière une requête ECL. Et donc, vous allez recevoir à ce moment-là une ressource de type ValueSet FHIR qui va vous contenir les résultats de votre requête ECL. C'est pas encore en place, ça sera en place bientôt. Je peux pas vous donner aujourd'hui de date précise, mais on va communiquer largement quand ça sera en place. Donc ces éléments, vous pourrez en effet passer des requêtes ECL via en réalité le serveur de terminologie de l'ANS, enfin national, et derrière vous allez recevoir des ressources FHIR qui vont comprendre ces value sets avec ces codes SNOMED.
I only understood about 10% of what you said, but you're right that the value sets are good for terminology binding and capturing the right information in the right fields. And maybe ECL isn't needed in France for that, but maybe for some of the other use cases.
Just explaining in French, but we are implementing a national terminology server, and with a FHIR request, you can put ECL constraints or ECL request and give back resources with SNOMED CT code inside, resources like value set or code system. This is not yet implemented. We are working on it. We will, of course, explain it and communicate when it will be ready.